Hello, welcome back. Today we are going to see the different activation functions. As you know, each layer has its own activation function. And we have different activation functions. It's usually represented using the sigma letter. And we have different activation functions. The first one is the identity. The identity is the simplest one. It is fx is equal to x, so it can be represented as a line with one slope. So this activation function is not really an activation function. The next one is the rectified linear unit, or ReLU. It can be represented as this max of 0 and x. If these are the axis lines, this function will be 0 if it is below to 0, and if we have x greater or equal than 0, the function will be x. So it's similar to the identity, but we have here a straight line. The next function that we are going to see is the Sigmoid, the most common function in neural network. Sigmoid. It is similar to the next one that we are going to see, and this function is represented by this 1 divided by 1 plus e to the minus x power. And this is a special function because the numbers that output this number are always between 1 and 0. So if we want to output a probability that it will be the perfect function, it is like this. I haven't drawn it really well, but it could be like this. Now the next function is the hyperbolic tangent, tan h. This function is similar to the sigmoid function, but it differs in something. The function goes between -1 and 1, so it is a little bit more deeper. This function tends to 0, and this function and this part to 1, and in the hyperbolic tangent we have a -1 here and a 1 here. So, and the last function that we are going to see is the Softmax, a common function in neural network. The Softmax is a little bit more complex because, wait one moment, okay, you have to take in account the other outputs. We have to sum the outputs to the output y, and we divide it to our output x, j. So this output will be divided by the sum of the other of all the outputs with in the exponent. This is our I, okay, and this is also an I. So that's all. These are all the activation functions that we can find in neural networks. There are also a few more, but the most common activation functions and the most popular are these. So we are going to implement each of these using C++ and coding it. So now we can start defining our files of the activation function. The first one will be the identity, that we will save it inside the carpen activation. Identity. We are going to include the eigen and the configuration of our project. The next thing that we are going to do is define our class identity. With a type def. Matrix scalar eigen dynamic eigen okay, that's we need to implement two main functions. The activation, the activate function, matrix set, and the matrix A. And it is really simple. A, no aliasing means is equal to set, no more. And we also need to implement the derivative or the Jacobian that we call when we applied a derivative to a function, and it depends on a few parameters. You may want to write that in a matrix, and that's called the Jacobian. Matrix, the set, matrix A, the cons matrix F, and the matrix G. Oh, sorry, I written that. So we need to multiply G, no alias, by the derivative of the function, and you know that the derivative of this function is 1. So we only we can write 1 multiplied by f or f instead, and that's all. The next file that we are going to include is the rectified linear unit. inside activation. We are going to include now every file. The Sigmoid, the hypertangent, and the Softmax. Okay. This is a tedious work, so we are going to copy in every file the thing that a template or something to make it more easy to us. Class okay, private type def eigen matrix scalar eigen dynamic eigen dynamic matrix line void activate matrix A and the function Jacobian inline void apply Jacobian to matrix set const matrix A const matrix F okay, we are passing by reference the elements in order to reduce the computation waste of resources. So that's more that's optimized in order to make it quickly. Oh, what happened? We copy, we paste. Okay, we copy, we paste, we copy, we paste. That's all. We can now implement the first one we are going to implement is the Sigmoid in order. We are going to do in order. Add.array is equal to 1 divided by 1 plus minus set array dot exponent okay to the minus set exponent. Okay, that's we write array to operate each element using this operation, and the Jacobian that we are going to do is you may not understand if you see right now but if you do the derivative of the function Sigmoid, you will achieve the same results. So to get to the Jacobian, we need to multiply the output by 1 minus the output. Okay, and we multiply that by f. That was the the previous value of our derivative. So wait, that's all. And we store in G. So that's all. Now we need to implement the hypertangent. That this is really easy. Is a array. Hey, what a moment. Is equal to set. Oh, the hypertangent that we have. We don't have to declare it because I forgot that. We don't have to declare the hypertangent because it's already defined in eigen. So the derivative of that would be 1 scalar 1 minus a array, and we multiply that by f. So that's all. But the real derivative you need to know is that we are applying to f that was the previous derivative step. And now we need to implement the softmax function. This is a little bit more complex. We also need to make a new type def that would be the array scalar 1 eigen hey, what a moment. Where are you going? The row array. Add array. We multiply using the row wise operation to set call wise max growth. Row wise. Okay. We define our row array that will be the sum of the columns, call sum a dot call wise dot sum, and now these operations means that you are doing the operation in each row. So to make the parallelization, it would be great. In the derivative, we need to define a row array, a dot f, that would be the Hadamard product of a or wise product. You can call it as you want, of a and f, and we sum it by and you sum the row each and you sum to every column. Okay. And the derivative is a little bit confused rowwise minus ed dot f. That's all. We have just implemented the 5 activation functions, so we can now save them. And this would be video 7 activation function. I remember you that you could download the project if you have lost something, or you need a file, and it would be in my GitHub repository that you could search that on the in the description of the video. So that's all for now, and see you in the next, where we will be implementing the different kind of error functions, the output layer. So see you. If you have any questions, don't doubt to ask it in the comment section.